Hello and welcome. Today I will show you how you can perform firmware update and Lua update using our backend service we have uh, via narrowband IoT. In previous videos I have shown you how you can do the firmware update and Lua update using our GUI, using serial interface. But today we will only use the serial interface to monitor what is happening. So in reality, if your device is in field, the serial line of course will not be connected. But to see what is actually happening, I will have the serial line connected, and you can see how it will look like when you will do uh, testing on your table of this process. Okay, so first of all, I will a little bit explain how the backend we have cooperates with the narrowband IoT connection which you use with our device. Uh, there are basically two or three options. One option is that you have an internet narrowband IoT SIM card, which means you are using APN, which will be uh, set, which will allow you to communicate directly to public internet. In this case, you have your narrowband IoT device. In this case, it is narrowband wireless M-Bus device on the picture. It communicates using UDP to your backend, and the way you can execute firmware update is that you will launch this little UDP proxy service, which acts basically as a man in the middle, and it forwards the traffic which is necessary to ACRIOS backend, and the ACRIOS backend can execute firmware update, and then you can turn off this service and you can send the traffic directly to your backend software again. Or you can leave it running and it will both send the traffic to your backend and to the ACRIOS firmware update backend software to execute the firmware update or Lua update. Other option is that you use Miotiq. Miotiq is Narrowband IoT connectivity provider. Uh, it allows connection in different countries, and it helps you to abstract um, the interfacing. It First of all, it keeps all the traffic in a private APN, so that it doesn't use its public internet, and then the communication from Miotiq to your backend is done via HTTPS post request, which can be set up, for example, like this in this case. Here you see the API key, but we don't show it here entirely because of security reasons, of course. Here you set up the URL for our backend, which is like this, and this API key, you can get it for your user from our backend after authentication, after clicking here. So I will show you that. Today we will use Miotiq SIM card, but for any either using public internet or private APN, but communicating using UDP to your server uh, inside a VPN, for example. You can use the same approach. The only difference is that you need to have this UDP proxy service running. Um, so, uh, but let's get back to Miotiq. How you get the uh, how you get the key? So we first authorize. So login and password, and we are logged in. And then we go to token, try it out, and we type here the uh, secret password. This account will be deleted after the video. If you want your own account, contact us at support@acrios.com, or you can write me directly at novak@acrios.com as well. And here I click execute, and here is the access token which you can use. And this access token is then input here in Miotiq, and it will work. When we create your account, we need this API key, which I will not click here so that I don't show you our production API key. But if you send us this API key, we can then communicate using Miotiq directly with your devices. So this is how it can be integrated with Miotiq, and then in Miotiq you can dynamically disable the endpoint so that the traffic is not sent anymore to our update backend, and then you can reroute it back to your backend. Or what you can also do, you can send all the traffic to our update backend and also to your custom backend for data processing. So this is one way how to do it. And the other way, which I should explain as well, even if we don't use it in today's video, is that you use UDP proxy. Uh, this article about UDP proxy and how it works will be published on Wiki, but for now I will show it in this PDF. So I already explained the principle on this picture, and you can see in colors the IP addresses and ports and what is used for what. On your server, so this big box is a customer server machine, so this is some virtual private server, for example. You have some IP and port where the IoT device, where the NWD, Narrowband Wireless Bus, for example, sends the ingress traffic. So you need the IP address and a port. In this traffic gets captured by the UDP proxy service, which needs the IP address and port of your backend software, which will be, for example, localhost and some localhost, some UDP port on the localhost, and then you need to have IP address of our server for the update. So here is the Dexter's, and also last thing which you need to reserve a pool of UDP ports. I'm using 50,000 to 60,000, which will be dynamically assigned for the proxy service. When the message is resent to the backend on a dynamically assigned port, the proxy service wait for the answer, which is then forwarded back to the device, and this is how the full firmware update can happen. Okay, so this is you can stop the video and read this if you are interested. And here is the script, which is also appended here, and you can see it's very short, but I will open it in something more reasonable, like VS Code. So here you can see the command bytes, and here is how you invoke the script. You can already see this is an example of how it can be started. So this IP is IP of your machine. This is the UDP port where the end devices send the data. This is the IP end port of our update server, and this is the localhost IP end port of your custom backend running on your VPS. Of course, you can use one VPS for the proxying, and this doesn't need to be a localhost IP, but this is like most likely the case. So that's why we have shown it like this. And last but not least is the range of UDP ports which are used for the proxying. All right, so let's get to it. So first, I will go to our backend and I will register the device. You can see here there is a SIM card, and I have already checked what is the IMSI number of the SIM card. You can check it in the you can check it either at some portal of your operator, or when you insert the SIM card in the device. I will show you that because it can be useful. You plug in the serial line and you open, for example, Qtcom on Linux. You can use Termite on Windows, or I think Qtcom is also on Mac. So if you are using Mac, you can use Qtcom as well. And after inserting the SIM card, you connect the battery, of course, and you should see the device booting like this. And after a while, you see here the IMSI. Yeah. Now I will turn it off so that and force it not to proceed further, because I just wanted to show you how to get the uh, IMSI number of your SIM card if you don't know it. Of course, if the device is in field, you need to know the IMSI. Otherwise, it would not be very good if you don't know it, because you would not be able to do the firmware update. But this is basically mainly for your table testing. So I will clear the serial output. So first, let's register our device. So we are already logged in. Now I will go to units, unit add, and here I can paste the IMSI of our device. And normally I would use the device type of wireless 868 MHz, which is used for our wireless M-Bus devices, narrowband wireless M-Bus. You can use also M-Bus for narrowband M-Bus, but here this time I will use other, because with other device type you can update not only narrowband wireless M-Bus or narrowband M-Bus, but you can update any narrowband device from ACRIOS. So I will put here other, which is more universal, and I will register the device. So we can see here result success, which means it works. And now I can quickly check also the unit identification info, which will give us some information about info about the device. So you can see that it is there, config state pending. You don't need to care about this because this is normally used just for the narrowband wireless M-Bus devices. But you can see it is there, it was registered, and that's it. So now we need to upload the firmware file. Normally you will not be allowed to do this yourself, but if you need to firmware update your device, you can ask us, and we have of course admin account, and we can upload the firmware for you to your account. But in this case, my my customer user is assigning to himself the firmware, so I have allowed this user to be admin. So this time I'm allowed to do it. So I type here the name of the target user to who will have access to this firmware. I select the new firmware, and here I type that the firmware type is custom. This means that uh, this confirmation, because how it works, we do the firmware update, and then the application boots, and when it boots there is some Lua script which sends some hello message on the beginning, and this is completely customizable. So for our applications the message is starting with F0FF, but if you are using something else, something custom, you can put here custom, and you can either put here in hex the beginning of the message which should be expected, which will basically tell the backend that okay, the update is done and we are finished, or you can also leave it empty so that it will accept any message which doesn't start with F9 hex or F7 hex, because F9 hex and F7 hex are command bytes which are used uh, by the bootloader. So we leave it like this, which is the most universal thing. We choose here the file and we upload it. It takes a while because what happens is that the file is split into parts, it is compressed, it is encrypted, and then it is a so-called chat script is generated, which is a set of requests and expected answers, which are then used during the firmware update. Okay, so we should see a success here. We are fine. We can also list the firmwares. So if we don't know the name, we can list it, and Oh yeah, here I made a mistake. I didn't put a name to the firmware, so let's fix that. So I will call it new FW. Okay, so let me fix this very quickly and go. There are some options like use quad SPI. You can change the transmission unit, so how much bytes is you send at once, what is the compression unit, but to keep it simple, just leave the defaults. If you for some reason need to send the firmware in smaller chunks, for example if the maximum transmission unit of your operator is smaller than 1 kilobyte, then just contact us and we can help you out. I think that the firmware update procedure we have developed and tested very massively in also in production, tested with different narrowband IoT networks. The reason why we design it and why it is configurable so much is that it is future proof and it can be really used on different networks with different MTUs. So that's why you have so many options everywhere. But for happy day scenario, just leave the defaults. Okay, I copy the name of the firmware and now I can schedule the firmware update. But before scheduling the firmware update, because what would happen, it would directly execute the firmware update when I start the device, because the device starts by first running a bootloader. If there is no boot request, then the device boots to the application, and only then um, uh, and then there is the application. Yeah, so I will first start the device without the bootloader request pending. So um, I will split my screen so that we see the serial line, and I will turn on the device so you can see the boot. Um, I will not it is registered and it is booting. So if there is no pending firmware update and it is registered to our backend, the backend will actively send a boot command so that it doesn't send again and again the boot request. The default is, I think, that it will request for 4 times, and if it detects that there is no valid firmware, it will request even more times. But you can see here it received the 4B message, which is big majuscule K in ASCII, which forces the bootloader to go directly to the application. You can see the version of the application here. It is 2.13.8, and because this is a development device, there is no serial number assigned to it. So we see it booting, and we can see here that it is sending the beacon message to our backend already. Okay, so what I can do now, I can leave it like this, or I can schedule the firmware update now. And what will happen? Message will be sent to the device, kiss of death message, which will basically cause the device to reset. Then the bootloader starts, and then the exchange of the messages happens, which will do the firmware update. You can see nothing was sent from the backend to the device because nothing is scheduled. This specific Lua script is actually expecting an acknowledge, but because I have selected the other device type, not the wireless M-Bus device type, it is not receiving any answer, so it is trying again and again. But this is a very specific application logic we have there. Just ignore this. This is just sending the requests. Okay, so I will now go and schedule the firmware update, which I can do like this. I go to firmware, I put here the identification of the device and here the identification of the firmware, which I of course forgot, so I will copy it from here, and now I'll put it here. Just leave the default and click on execute. So now you can see that it is trying to send this beacon message, so-called beacon message, in this specific Lua script, and now it's trying again after 5 seconds, after 25 seconds. So I will schedule it so that the next request, on the next request, the device will receive this kiss of that message as answer. Normally, with wireless and bus mode, it is not using this internal kiss of that message, but instead, yeah, this is the message. You can see it. this exactly 51 bytes, and it is starting with these bytes. And it must be it must be exactly this, otherwise it will not reset. And here you can already see the bootloader running, so I will leave it running. I was just saying that if we used the wireless M-bus device type, it would instead use the command byte 7, which is reset, and it's implemented in the Lua script that it actually resets after receiving 7 as command byte. But if you just forget to handle the reset command in your Lua script, the only thing which is required is that you have enough receive timeout, so not like 10 milliseconds, but at least maybe 5 seconds or 10 seconds to be safe, and not always, but it's okay. It is like that from time to time, and this way you can receive this case of that message, which will trigger the device to reset. And once it resets, then there is a safe configuration used by the microcontroller, and this, between the microcontroller and the narrowband IoT modem, and it asks for new firmware. And that's when the backend comes and sends chunk by chunk the whole firmware. You can see the progress. You can because normally you don't have access to the serial line, so you can't see the progress like that. But if I copy the IMSI, I can check the progress here. So first I can go to unit info, and I see here the bootloader request, the last received bootloader request. There are some CRCs which can be used to verify what actually happened. I can see the flash size, because in the future we plan to switch to 512K, so we are already future proof from this perspective. And here you can see the running firmware update. If you are even more curious and you want to see how far you are during the firmware update, you can check this endpoint /update, and here uh, you see uh, you see that it is running, and it is at command sequence index 22. Yeah, if I refresh, it will be at 24. So maybe you don't trust me, it is actually running over Narrowband IoT. So what I will do now, I will disconnect this serial line, so you can see that the printout just stopped. There is nothing printed here. Just to make it interesting, you maybe saw this. So it is how it works. It is it first receives approximately 24 kilobytes of compressed data. Then it by sending this command, it executes the decompression and deciphering, and then it flashes uh, part of the uh, part of the device, and then it continues. And the algorithm is quite robust, because even if some part, for example, doesn't pass this, or if the device resets in between, it retakes where it ended. Yeah, so it doesn't repeat the whole firmware update, and it also executes checksums and CRCs for the whole firmware, but also page by page. So it is, I must say, I'm quite confident that it's a robust process. So okay, we see the serial line is disconnected, and I will now click on execute to see a refresh, and we can see it is already at 39. I connect it back to see actually that something is happening. So I plug it back, and yeah, so we can see it is actually running. 39, 43. Yeah, looks like my cable is a little bit tricky, but yeah, it continues running, and here the index is being increased. So now maybe we will skip this part in the video, because we from the experience, this will go until approximately 180. So we would need to wait for a quite long time, which is not the case of the Lua update. You will see it's really fast. So now I will let's skip this part just so that you are not bored. Okay, so we should be heading to the end. You can check the timestamps on the serial line. Okay, yeah. Now this 43 command is check of the CRCs, and 4b is a command from backend to boot. So we can see here, if I check the status, that we are at 183. It is still running, and after it receives the first, yeah, this is the printout of what happened before the reset. Yeah, this thing, and now it's sending the error report. That's how it is done in our custom Lua script. And it's sending the information to the backend, and after sending these messages, it switched status to done. And you can also see it here in the info that it changed from firmware update request from running to done. Yeah, so now it is updated. What's also interesting, if we check here, um, so this is the last reset message. So exactly what happened just before the reset, and because this is stored in a special place in RAM, this place is analyzed during the boot up, and uh, the Lua script sends the last reset uh, information automatically to the backend. So it is possible, if from some reason the device resets, with this Lua script we call it multi-mode, wireless and bus and double and NB-IoT. You can see that you can see what happened actually, what happened just before the reset, which is quite handy and not common for embedded devices. You can see that the version changed from 2.13.8 to 2.13.9, and the Lua script is reporting here wireless and bus and NB-IoT version 14.8, which is version not of the firmware, but or we can call it a virtual machine, but or Lua virtual machine, but version. But this is version of the Lua script, which is running on the firmware, which is running on the Lua virtual machine. Okay, what we will do now, yeah, the firmware sent all the reset report, and now it is trying to send the beacon, but it is not receiving any confirmation from the backend because it is not registered as a regular wireless and bus device, but instead it is registered as other. So it is ignoring any message which is not bootloader request, so that it doesn't interfere with your backend, which can be there. I just recall you. Yeah, so it is ignoring any other message which goes here, and it is not sending any answer, so that it doesn't interfere with the communication happening here. Okay, now I will show you how we can do a Lua update. So we will first add the Lua here. This you can do even if you are not admin user. So we will call it, for example, new Lua. Use bootloader. Here I will put true. It is possible to do the Lua update using the application firmware as well, but it is faster to do it using bootloader. And we keep this option, but it is getting legacy now, so use bootloader true is the future. Here I select new Lua script, which has some modification inside. You will see it after the update. So the print after the reset will be different. And I click on execute, and you can see it was uploaded quite fast to the backend because it is much smaller compared to the whole firmware. Now I go to the unit and I go to Lua. I click try it out. I put here the name of the Lua script, and from somewhere I can here list, for example, all the units. Yeah, I get the IMSI of our unit, and I put it here, so I have the IMSI, the name of the Lua script. I click on execute, and it is queued and scheduled. Now we wait until the device wakes up and tries again to send the beacon message, and after that, but it doesn't need to be beacon message, it can be basically any message. It will receive a request for reset, and the bootloader will start, and the whole update will happen. We can again go here and check in update endpoint. If we click execute, we can see here that it is pending and it is at index 0. We can theoretically speed it up by clicking the button, but let's wait, because I think it will be only just a couple of seconds now, so I will not touch it, so that I doesn't interfere anyhow physically the process. In the meantime, I can show you that you can also see log of all messages received by the backend from the device. You can filter them, and you can also filter them by time, so that's what I will do. 2024 02 14 time 12 15 00. Execute. Yeah, since until it looks like I did something wrong. Yeah, I think it has to be in UTC maybe. Yeah, and here we can see the messages which were sent. You can see that there are some beacons sent with the timestamp, and here it received already the reset. So if I maybe, yeah, we are UTC +1 now, because we are the winter time, and here you can see what was sent up and down. So we have a complete log of timestamps and of the messages which were sent up and down. You can see that the Lua update process is very quick, so I could, for example, keep clicking here and seeing what is sent up and down, or I can go to, yeah, you can see that the message was sent there and there was a confirmation, but I can also go to /update and observe what's happening here. Actually, why I'm using always the /update is because the /update is a universal tool which allows you to send a command sequence to the device with the requests and expected answers. And the Lua update and firmware update are actually just the shorthands which allows you to effectively and efficiently send Lua and the firmware. But you can also send to the device your own sequence of messages with your own sequence of expected answers, but that's quite specific, so I don't think you will try to do that. We can show that in some future video if it is required. But most likely what you would like to do is to update the firmware, or even better, just the Lua script, because it's much faster. And if you compare the number of time spent updating one or the other, it's much lower, the time spent, and also the amount of messages sent up and down. So now it was flashed, and I must say that this is quite a big Lua script. Yeah, so it's flashed and it's already booting, and we should see here a different printout. So it's going, yeah, and it is working. We have the printout here, and also what changed is the version of virtual version of the Lua script, because this version is actually hard-coded in the Lua script. It's just for some, let's say, internal management, so that we know what version is there. So it's a good practice to put there some version. But this is the proof that we actually uploaded the file I've shown you. I can also show you the file itself. Yeah, well, we have the VS Code here, I think. So yeah, this is the new Lua script. You can see the version here, and you can also see it. You can also see it here. We printed. It is working in the on startup function. So yeah, it worked. and you can yourself, you can update the Lua script, you can change it, modify, and re-upload it again and again as much as you can. Um, and for the firmware, ask us if you need us to upload the firmware. So thank you for watching. It was quite long today. We will speed up some parts, and I'm looking forward for making future videos for you. Bye soon.